We understand that light is a wave, and one of the reasons we know that light is a wave is that it undergoes interference patterns. Remember that this is when we have constructive and destructive interferences, and when we take any wave, and it doesn't matter if it's light or with an ocean, and we allow a medium to go up and to go down at the same time, it is either going to take and make smaller waves, or it's going to go up at the same time and make bigger waves. And one of the ways of doing this is putting it through a slit pattern, but this is an interference pattern for light. We know for sure light is a wave. Now, that was all well and good until the physicists tried to understand black body radiation. All right, we've seen black body radiation. We went to the lab and we looked at magnesium, and we looked at magnesium in crucibles. And when we heated them up with a Bunsen burner, we discovered that our crucible, when we had our Bunsen burner flame underneath it here, got very hot and it was red. And it didn't matter whether or not it was the crucible or whether or not it was the sample on the inside of the crucible. It all glowed the same shade of red. That is black body radiation. Now, this has been observed for a long time, but the physicists obviously tried to figure out why, what was going on with black body radiation. So, Max Planck took a look at black body radiation, which is just simply the statement here that things glow. And things glow a certain color depending on the temperature. So things glow a color and it depends on the temperature. Red could be cooler or is cooler, orange is hotter, yellow is hotter than that. Stars that are white are very, very hot. So why am I showing you this instead? This is a string that is on a fixed end. This could also be on a resonator. This could even be a guitar. What we have here is a string that, instead of being sort of like a piece of rope that you could wiggle, which is what we were talking about previously, this is fixed. Once we do, and we have a fixed wave, we're going to call this a standing wave. So if we have a standing wave, it's fixed on two ends, and once you have a wave that is fixed on two ends, only certain waves fit. So notice that I can put one wave forward and backwards, or I can put a wave going forward and back with a node in the middle. A node is where, if you looked at it, it would appear not to be moving. Or I can put, in this case, 3 waves or 4 waves on this string. Now, why does that matter? Well, it matters because if I try to take this string and I tried to put this wave on it, this wave would not fit. Only certain waves can fit when you have a standing wave, and all a standing wave requires is fixed in. All right, well, this is simply a mathematical prediction of black body radiation, and this is saying if you have a certain temperature, it is going to glow a certain color. So if we had colder, which is this one down here, it's going to be redder. If we have hotter, it's going to be down here and bluer. And again, this here is the math behind this, things glowing because they're hot. If we compare this to the sun, the physics, which is right here, and what we observe from the sun are pretty darn similar. And we say that the sun is glowing, and it's glowing at around this temperature because it's hot, giving this yellow orange, and that the math, which is this line, works pretty well with our experimental evidence. So why is this relevant? This is relevant because in order to make sense of this, the only math that they could use to make that physics work was to say that the light that is in the sun is quantized. Quantized is very specific. Quantized means only certain energies. Where do we see certain energies or quantization? We see this with standing waves. Standing waves are the waves that occur when you fix the ends of the string such that you will fit maybe this wave or this one in, but not all wavelengths were fit. And when Max Planck said that we're going to do this, he said that our energy of the light that we see is equal to n, where n is a whole number. N is 1 or 2 or 3, and this would correspond to n equals 1, and this would correspond to n equals 2. It's just a number. And E is equal to n times h. H is Planck's constant. It has this value, and n, we're going to discover, is the number of photons. But this is simply the equation you use to make it work, for which you got a Nobel Prize because it's pretty slick. Check out this video of quantized standing waves. It's very cool. It's sound, and I'll describe it a bit later on. All right, let's look at a laser that has a wavelength of 633 nanometers. We have a couple of equations when we're trying to figure out the energy related to the wavelength or the frequency, and our equations are this. E is equal to nh nu, but we also know that C is equal to nu times lambda, so we can rearrange this and get E is equal to nhc over lambda. Because we're working in wavelength, we're going to use this one. So we have 1 mole. We know that 1 mole is 6.022 times 10 to the 23rd. We're going to have to use that number. Remember, 1, it does not mean 1 each of something. 1 mole is a great deal. We've got to include that. So E is equal to 6.022 times 10 to the 23rd, multiplied by Planck's constant, 6.626 times 10 to the minus 34 joule seconds, multiplied by the speed of light, 3 times 10 to the 8th meters per second, divided by the wavelength. The wavelength here is 633 nanometers, multiplied by 10 to the minus 9 meters per nanometer. Yes, I know that's a lot of math. And when you finish that, you're going to get 189,000 joules, obviously to 3 sig figs, or 189 kilojoules. Let's do part 2. We're given the photons here, and we can plug in a number on the photons rather than 1 mole. And when we do that, we're going to get E is equal to 3.45 times 10 to the 24 photons. It's bigger than a joule, so our energy is going to be, or bigger than 1 mole, so our energy is going to be higher, multiplied by 6.626 times 10 to the minus 34 joule seconds, times again 3 times 10 to the 8th meters per second, divided by the wavelength of 633 times 10 to the minus 9 meters, combining those two steps, giving us a great deal of energy, 1.09 times 10 to the 6th joules, or about a megajoule. So we can convert from the wavelength here into the energy of this light. All right, we're going to calculate the energy of 1 photon of this X-ray. And yes, if we look at this value, this is shorter than ultraviolet, longer than a gamma, and this is in the X-ray region of the electromagnetic spectrum. So we're going to start with that. So step 1, if we want energy, E is equal to nhc over lambda. This is 1 photon, not the same as 1 mole, is equal to 1 times Planck's constant, 6.626 times 10 to the minus 34 joule seconds, multiplied by the speed of light, 3 times 10 to the 8th meters per second, divided by the wavelength at 0.154 nanometers. We know that there are 10 to the minus 9 meters per nanometer. And this is going to give us 1.29 times 10 to the minus 15 joules, which isn't very much. This is only 1 photon. Now, obviously, if we had Avogadro's number of photons or 1 mole, it'd be a large value. Let's do this in a different direction. Let's figure out how many photons, what our n value is, with 325 joules. In this case, we know E, and we're going to start out with 325 joules. This is going to equal the number of photons, and the rest is exactly the same. 6.626 times 10 to the minus 34 joule seconds, multiplied by 3 times 10 to the 8th meters per second. Because this is 3.00, I'm just leaving the 00s off of this, divided by 0.154 nanometers, multiplied by 10 to the minus 9 meters per nanometer. When I rearrange and I solve for n, I'm going to get 2.52 times 10 to the 17 photons. All right, so what have we done? This time we have converted between the total energy of all of this light into how much light we have. Now, we've talked about photons, or we've used this number without actually explaining it. So that's next. So to explain what a photon is, we are going to go and we're going to look at Albert Einstein. Einstein took a look at the photoelectric effect. So, photoelectric effect, which you think you don't know what it is, but trust me, you have seen this, because all this is a solar anything. In particular, let's imagine that you have a solar-powered calculator. This is a classic example of the photoelectric effect. Photo means light, electric meaning making electrons. So let's take a look at this. The photoelectric effect we can see as we shine light of different wavelengths onto a surface. And so what we need to imagine here is that we have some piece of metal, and we can start out by saying we're going to take and shine red light onto it. And if we shine red light onto it, we're going to see whether or not we can get electrons. So let's imagine that we know what we know about light, and that is that light is a wave. So we have shown so far that light undergoes constructive and destructive interference, and light is a wave. And they found that if they put red light onto this surface, they got no electrons. So if we don't have any electrons with this wave, first thing we're going to do is we're going to hit it with a bigger wave. Because if light is a wave, then a bigger wave is going to have more energy. So let's think about that. So now we have a new surface. So down here, we have a new surface, and we're going to take and we're going to shine this low or dim red light with some really bright red light. And we found in both cases there were no electrons. And that puzzled physicists, because if you hit this surface with a bigger wave, it should be like a bigger wave on the ocean, and you should have enough energy for the electrons to come out. Didn't happen. What happened instead was that if you took and went to a shorter wavelength, rather than what appears to be more light, you went to a shorter wavelength, and as they went to a shorter wavelength, electrons came out. And what this tells us is that a wave like this has more energy than a wave like this, that the energy is not carried in the amplitude, the energy is carried in the frequency. And Einstein said, all right, this is not an issue. We understand this. And we said that instead of light being a wave, because if light was a wave, then big waves like this would kick out electrons. He said light is a particle. Light is a particle such that E is equal to NH nu, where N is now the number of particles. And if we look at it, this is consistent with what we're seeing, that our energy depends on the frequency, not on the amplitude.